Hi students, in this video we are going to discuss the questions of surface tension. We'll start from the very basic question and then slowly we'll increase the level of the questions. Now the first question is, one figure is shown, this is the diagram shown. It shows the container of radius r, this is radius r. It is filled with water and you consider an imaginary diameter line, this particular line, this line, dividing the surface in two parts, left half and the right half. This has been divided in two parts. We have to find the surface tension force between the left part and the right half surface. It is something you can say the situation is like, this is the surface and this is the diameter line. Now along this line, how the force will act, left half will pull the right half in this direction with a force given by S into length of this line, and this length of this line is nothing but equal to 2r, so S into 2r. And similarly the right half will pull the left half in this way, right? So the required force will be equal to surface tension into 2r. Easy conceptual question. Let's take the next one. Consider a water drop of radius r and we have to find the surface tension force between the left half surface and the right half surface. This is also a nice question conceptually. If I say you consider one water drop of radius r, it is like this, it is spherical drop, and they are saying find out the force between the left half and the right half. They are asking what is the force exerted by right half part on the left half part and vice versa. Now here if we see this particular surface, if you imagine that this hemispherical surface you have cut in this way, from here you have cut this way, then on the boundary of the left part will be this green circle. This particular part will be pulled by the right part and the force will be acting in this way along the tangential to the surface. And what will be the length of this particular circle? 2 pi r. So the surface tension force by the right half on the left half is equal to S into 2 pi r, and same by the left part on the right part also. Not only this, if somebody asks what is the force exerted by upper half on the lower half, means what is the force exerted by this portion A on the B due to the surface tension, then force will be in this direction, upward, and it will be S upon 2 pi r. Not only this, if I extend the question to some other level also, let us say somebody asks this is a spherical drop of radius capital R and we are considering only at a distance of small r, we are considering this part, means only this part has been considered. What is the force exerted by this part A on the part B? Then the force, how the force will act, try to understand. It is nice one. Now here the force will be acting in this way along the surface everywhere. say if its radius is y, radius of this circle, pink circle is y, then 2 pi y into s, that will be the force in this direction. Then after that we have to resolve it, and this particular component, the particular component will be cancelled. This component is going to be, this component will be cancelled, and only this component will be left over. So say this particular angle is theta, then the force with which this part A is pulling the part B will be S into 2 pi y into cos theta. This will be the force, and theta value you can find easily by using the mathematics, right? It is again a very nice question, conceptual questions. Next you take between a frame and a light slider. There is a frame, this U-shaped frame, this frame, and a light slider, and this is the slider. This is the slider. A thin film of soap solution, a thin film of soap solution is made. This is the soap film, whose length is x and the width is y. This is given. We have to find the surface tension force on this slider to keep the slider in equilibrium. Now on the slider, what are the forces acting? One acting mg downward, and in the soap film there are two layers, two surfaces. So the force acting on the slider due to the soap film will be S into x, and two films, that's why into 2. So what we can say, on the slider two forces are acting, one mg downward and S into 2x upward. To keep the, okay, it is given light slider. So, and they are asking to keep the slider in equilibrium, how much weight should be suspended. Let us say the weight suspended is m, then mg will come. Its own weight is not there because it is given in the question, it is light slider. So mg downward, S into 2x upward. So m will comes out to be S into 2x divided by g. This is the mass what we have to suspend it from the slider. Take the next question. Consider a bubble of soap solution. Consider one soap solution bubble, and we have to find the surface tension force between the left half surface and the right half surface. This question is very much similar to previous one, second question. Now here what they are saying, it is a soap bubble. Earlier we were considering the liquid drop only. So here two surfaces are there. Forces will be acting this way. One on the outer surface. Always remember, surface tension force acts along the tangential to the surface, and other will be on this inner surface. Now the thickness of the soap bubble is very small. So the radius of both the bubbles, both the surfaces are almost equal. So this one will become S into 2 pi r. And this one also become S into 2 pi r. So what is the total force exerted here comes out to be? S into 4 pi r. This is the force exerted by the left half on the right half and vice versa. Take the next question. This is also a very nice question. First I'll explain the question. What is the question? A thin disc of radius r. This is the disc of radius r. Just touching the liquid surface. It is just touching this liquid surface. Forms one arm of a balance, and it is forming one arm of a beam balance. The plate is balanced by some weight on the other side of the balance. This plate disc is balanced by these weights on the other side. How much extra weight should be added? They are saying how much weight we keep it here, how much extra weight we keep so that the disc just comes out of the surface. Now what happens? You try to understand it. Now it is just balancing. Now as we try to pull it, then this particular part, liquid, will try to pull it back because surface tension force will start acting in this way. If I say throughout SDL, 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 tangential to this liquid surface. Now under the assumption that theta is, the contact angle is 0. Under the assumption the contact angle is 0. Then the liquid surface will have the situation like this way. Then the surface tension force will be acting in the vertical downward direction. S into 2 pi r. So the surface tension force will be in the vertical downward direction. S into 2 pi r, which has to be balanced by the extra weight here, that is delta m into g. So what is the extra weight we have to keep at? S into 2 pi r divided by g. This is the extra weight we have to substitute, right? Take the next question. Next question is also very much similar. Now, in the previous question, in place of disc, a ring has been used. Now, in the previous question, we have used the disc, but in this question, we have the ring. This is the ring. Now, whose inner radius is R1 and outer radius is R2. And its inner and outer radius are given. Means earlier we were having the disc solid, but now we have a ring like this. Material is here only, right? Now how much extra weight should be added on the other side so that the ring can just come out of the water? Same concept, but here now what you have to see, if you have this object, this way, and here we have the material, and when it has been dipped in the liquid surface will be like this way, as well as liquid will be here also. I will make again this curve. Now surface tension force is not only acting on this green periphery, it is acting on the red inner periphery also, and hence we have the total surface tension force here as S into 2 pi R1 outer one, and on the inner one S into 2 pi R2. So the net total force S into 2 pi R1 plus R2 has to be overcome by the extra weight. So here the extra weight will be given by this particular expression. I hope you have understood the difference in these two questions. Take the next question. In this question, it is given a long thin straight uniform wire of negligible radius is supported on the surface of liquid. One thin film wire is there, like this one, which is supported on the surface of a liquid. Width of the container is given as 2d. This is given as 2d, and the wire is kept at the center, parallel to its length, means it is into the paper. Surface of the liquid is depressed by a vertical distance y. Because of its placing, the surface of the liquid depressed too comes down by a distance y at the center as shown in figure. If the wire is having the mass lambda kg per unit length, means if the wire is having mass lambda kg per unit length, say per meter, what is the surface tension of the liquid? And they are telling ignore the and effects. We have to find this. Now what is happening? This is the front view, two-dimensional view of the situation. Let us say you place one particular something like this, and on this you are keeping the wire like this, and you are observing it from this side. Then what you will see? On this surface, this cylindrical wire, because of its weight now, this depressed by y, what has been told, means if initially it is like this, it depressed by y. Now as it depressed by y, what are the forces acting on this particular part you see? The forces acting on it are, again I am taking the contact angle 0, the surface tension force, anyway here contact angle not mentioned, that's why we can take S into L. If this is the length, L is the length of this wire, then S into L this side, SL this side. Say this angle is theta, this angle is theta, then this force will come out to be 2SL cos theta sin theta component. SL sin theta, SL sin theta, total comes this. And this has to be balanced by mg, that is lambda L into g. So for the equilibrium we can say lambda Lg is equal to 2SL sin theta. Now in this triangle sin theta will be what? Sin theta is perpendicular upon hypotenuse. This is given as, separation is given as 2d. So this is d and this is y. So this will become y square plus d square under root. So sin theta is y upon under root y square plus d square. So you solve it, you will get the value of surface tension. Surface tension value we can calculate. L cancel, lambda g upon 2y under root y square plus d square, that we have written as approximately d, because it is given y is much less than d. So this way this question can be solved. Take the next question. If a number of little droplets of water, each of radius r, collects to form a single drop of radius capital R, then show that the rise in temperature will be given by this, where T is the surface tension and J is the mechanical equivalent of T. And it is also given R and capital T all in the CGS system. So concept we'll see. Some little droplets are there, say n, each of radius r. They form a single drop of radius capital R. Then because of this phenomena, temperature of the system is rising. Why temperature is rising? Because here the surface energy is going to change. That change in surface energy is appearing as the internal energy. So from the conservation of mass we can say n into 4 by 3 pi r cube equal to 4 by 3 pi r cube. Since density is constant, rho will be cancelled. So conservation of mass or conservation of volume, anything you can say. So here you got the capital R equal to n to the power 1 by 3 into small r. Right? Now what is the change in surface energy? That is equal to final surface energy is 4 pi r square and initial energy is n drops, and each is having the surface area 4 pi r square into T. Change in area into surface tension. So it will become 4 pi. If we substitute the capital R as this value, then n to the power 2 by 3 minus n, small r square will come out, r square T. This comes out to be the surface change in surface energy. This change in surface energy is appearing as the internal energy, which will change the temperature of the. It can be written as ms delta theta. This is the change in temperature. Now m can be written as n into rho into 4 by 3 pi r cube m. Specific heat capacity S into delta theta. Right? Now already they have given the expression in terms of small r and capital R. So this n is no need to write. So we can replace that also. And we will get here that change in temperature is equal to pi. It is better to leave the expression in this way only and no need of writing this n here. So 4 pi r square minus n r square upon 4 pi will be cancelled into 3 upon n rho 4 pi r cube into S. This comes. Now SS, if SS given in what we say in calorie, then we have to multiply it by S or J also, and the droplets of water, and for the water the value of S is 1 calorie per gram, so we can replace it by 1. That's why in the expression what we have to prove, it is not there. So 4 pi cancel and S can be replaced by 1, and what we are having here is r square by 3 j and T I missed here, T r square minus n r square upon n r cube. So this way you can have the expression, right? And n can also be replaced by using this particular expression. N r cube is equal to capital R cube. So this can be written as capital R cube and can be solved easily. This is already we have done in the theory part also. Now one more question we can take. Glass plate is there of length 10 centimeter, breadth 1.5, thickness 0.2, weights 8.2 gram in air. Now it is something like no, not this way. It is like this. Glass plate, length 10 centimeter, breadth 1.54 centimeter. Actually this is 1.54, and or this you take thickness at 0.2, and this is the width I am taking as 1.54. Weights 8.2 gram in air, means its mass is 8.2 gram. It is held vertically with the long side horizontal, this long side horizontal, and the lower half underwater. This particular part, say up to here, this part is inside the water. This part is inside the water. Find the apparent weight of the plate. We have to find the apparent weight of the plate. Surface tension given and G is given. Now in this apparent weight, one is mg, one is the buoyancy force. But along with the buoyancy force, there is a surface tension force also. Here the liquid surface is like this way. So liquid is pulling it down, and this surface tension force will be on this side, and this side. So the surface tension force will be mg minus buoyancy force, apparent weight will be equal to mg minus buoyancy force, and this is downward, so plus s into how much length? This 10, this length, this length, this one, and this one. So total it will become 2L plus 2 into thickness, 2 into 0.2 centimeter. So your expression will come S into 20 centimeter plus 2 into 0.2, that is 0.4. This will give you the apparent weight of the plate, right? So that's all for now. In the next video we'll discuss some more questions.